topic of this lesson is exponent rules and scientific notation. Here we have all of the exponent rules that we'll be covering in this course, and we'll practice some examples of each one. With the product rule, you can see that the base of a is raised to a power and multiplied by another base of a raised to a power. So the rule is to add those exponents when those bases are like bases. For the zero exponent rule, when you have a base raised to the power of 0, that will equal 1. Sometimes we will get answers other than 1, and that's only because other operations might be happening to a. So we'll explore that. With the quotient rule, you can see the problem is written as a fraction. So quotient, remember, is division. So a base raised to a power divided by a like base raised to a power shows the exponents are being subtracted. In actuality, what's happening is when the base moves across the division bar, the sign of the exponent will change. We started with a to the positive n, and when that base and exponent shifts to the numerator, you can see the sign of n changes now to minus. The negative exponent rule allows us to rewrite a base with a negative exponent so that the exponent will be a positive number. And most of the time, that's how we want to write our exponents, with positive numbers only. Our exception is when we're using scientific notation. So if we start with a raised to a negative exponent, think of that as a to the negative m over 1, and we're writing it as a reciprocal. So a to the minus m shifts to the denominator. Notice the sign of m changes. With the power rule, we have a base raised to a power, which is then raised to another power. So a to the m raised to another power means we are multiplying the exponents. With power of a product, that simply means we have more than one base that's raised to the power. So make sure that each base that's in the quantity is raised to the power. And finally, power of a quotient simply means we're starting with a fraction raised to a power. So both the base in the numerator and the base in the denominator will be raised to that power. So let's try some example problems to practice using our exponent rules. Our first exponent rule is the product rule. So again, here is the rule. Base of a to the m times base of a to the n means we're adding exponents. So as long as we have like bases, like we do here, a and a are like bases, we will add the exponents. So in our first example, x to the 7 times x cubed, we have like bases of x. So we just copy that base, and the rule is to add the exponents. So 7 plus 3. So this will give us x to the power of 10. Next, we have y times y squared times y to the 4th. So all the bases are y. So we keep the base of y. The rule is to add the exponents. So on this one we need to be careful because with our first base of y, it doesn't look like any exponent is given. So when nothing is written, it really is positive 1. So we have 1 plus 2 plus 4. So that makes y to the power of 7. In our next example, notice this time the base is not a variable, it's a number. As long as those numbers are the same, we're still following the product rule. So the product rule says to keep the common base. In our situation, it's 2. And then you add the exponents, 2 plus 3. So 2 plus 3. So that means 2 is raised to the power of 5. Since 2 is an actual number, we can further evaluate this problem. So it means 2 times 2 times 2 times 2 times 2. So you can either do this on your calculator or work it out by hand. 2 times 2 is 4. Another 2 times 2 is 4. And then times another 2. 4 times 4 is 16 times 2. 16 times 2 makes 32. So the final answer is 32. Here we have the zero exponent rule. When your base is raised to the power of 0, that will equal 1. So in our first example, x to the 7 times x to the 0. We do have a common base of x, so we could use the product rule and say x to the 7 plus 0, that equals x to the 7th. Or we could see it as x to the 7th multiplied by x to the 0, we know is worth 1. So x to the 7th times 1 is still x to the 7th. So we actually have two options to work out this first problem. In the next problem, you can see we have y times y to the 0 times y to the 8th. Remember, y is really y to the first. Y to the 0 is worth 1, and then we have y to the 8th. So if we multiply these together, it's y to the first times y to the 8th. Now we're using our product rule again. Y to the 1 plus 8 gives us y to the power of 9. In our next example, this time the base is a number instead of a variable, so the rule still applies. If the base is raised to the power of 0, then it is worth 1. Now the next part is a little trickier because we see 2x to the 0. So you have to think, what is actually being raised to the power of 0? And that would be only the base of x, not 2. If 2 were to be included, it would need to have parentheses to show it's included. So we really have 2 times 1. So this answer is 2. And we have something similar here in the last example. We have negative 2 to the 0. So only the base of 2 is raised to the 0, not the negative. There's no parenthesis to include that negative. So we actually have a negative multiplied by 1, which is negative 1. So what I was talking about earlier, sometimes we have answers other than 1 when a base is raised to 0. And that's only because there are other operations happening to the base. In this last example, a negative was being multiplied by the base. In this example, 2 was being multiplied by base of x. So we have answers other than 1. Here we have the quotient rule. With the quotient rule, we're starting with a fraction. We have like bases. So what was really happening here is a to the m is multiplied by 1 over a to the n. And then a to the m was multiplied by a to the minus n, because the term in the denominator shifted across the division bar, and when that happens, the exponent changes its sign. So it started out originally in the denominator positive and shifted to the numerator now as a negative. So notice we have product rule. Both bases are a, so we have a to the m plus negative n. Well, m plus a negative is the same thing as m minus n. So that's where the rule originates from. Looking at our examples with the quotient rule, x to the 7 divided by x to the 4th really means we can take the term in the denominator, shift it into the numerator. So we have already x to the 7 in the numerator, and it's being multiplied by x to the 4th shifting. So when that happens, the 4 becomes its opposite sign. So both bases are x, and we're adding 7 plus negative 4. So that makes x cubed. In the next example, our bases are numbers, but the rule still applies. We're keeping 3 to the 7th, and we'll multiply it by shifting 3 to the 4th into the numerator. So the base of 3 remains, but positive 4 when it's shifted, becomes -4. Notice both bases are 3, so we keep 3, and the rule says to add the exponents. So we have 3 to the power of 3, and since 3 is a numerical base, we can break that apart as 3 times 3 times 3. So that makes 9 times 3, or 27 for the final answer. Now the next two examples are just a little more involved because we have different bases here for the numerical portion. So think of this as 20/4. If you can reduce the fraction, then go ahead and reduce the fraction. So I know that 20 is divisible by 4, and so is 4. So if I reduce, I'll have 5/1. So I know that 5 will be in the numerator, 1 will be in the denominator. Now I'll work with the variable bases. Well, x is our only variable. According to our quotient rule, I can take the term that's in the denominator and shift it up, and the exponent of +5 will be -5. So I had x to the 6th, but now I also have x to the -5th. So when I simplify this, do you notice how we have division of 1 in the denominator? Well, if you divide by 1, you're not going to change the value of your terms. So to simplify this, we are not leaving division of 1. Everything collected in the numerator, 5x to the power of 1, which we just write as 5x. In the last example, again, we've got some numerical coefficients, 12 and 14, and they're even numbers, so they're at least divisible by 2. And that's probably all, because 12 would be 2 times 6, and 14 would be 2 times 7. So we could reduce the 2, and this time our fraction, we're going to have 6 in the numerator and 7 in the denominator. Now let's look at the variables. I have some bases of y and some bases of z. So I'll just start with y. When I shift y to the 8th to the numerator, I already had y to the 10th up there, and now I'm going to have y to the -8th. With the bases of z, shifting z to the 7th into the numerator, well, I already have a z to the 7th, and when this other base shifts, the +7 becomes -7, so times z to the -7. Now you can see 7 plus a -7, that's going to make z to the 0. And z to the 0 is 1. So what actually happens is the base of z is completely eliminated from this problem. We still have 6/7, and we still have some base of y. So 10 added to -8 would make 2. So we have 6y squared divided by 7. With the negative exponent rule, if our base is starting out in the numerator with a negative, think of this as a to the -m over 1, and you are shifting a to the negative exponent down across the division bar now. We just finished shifting everything into the numerator, but now we're going to shift into the denominator. Look what happens. -m shifting across that division bar changes the sign of the exponent. So that's all we're doing. Wherever you have a negative exponent located, simply shift it across the division bar, and that changes the sign of the exponent. With y to the -2, think of that as y to the -2 over 1. So to change -2 to a positive, simply shift it down. So we have 1 over y squared. In the next example, think carefully about which base is raised to the power. Only x is raised to the power, not 2. So we're going to keep 2 in the numerator, and only the base of x will shift to the denominator, and the sign of the exponent changes now to positive 6. For the next example, we have some numerical coefficients and we have variable bases. So starting with 24 and 8, both of those numbers are divisible by 8. So 24 divided by 8 will leave us 3. 8 divided by 8 will leave us 1. So that gives us 3x to the minus 3 over x to the positive 5. Now we're not quite finished because I still have the base of x written twice. That's how you can tell you're not finished, because you should not have any bases written more than once. So what I need to do here is, what we have been doing is shifting the denominator automatically, right? We've been shifting that base. So if I do that, I'll have 3x to the minus 3 multiplied by x to the minus 5, which is 3x to the minus 8. That is not finished because I have a base raised to a negative exponent. So just the base of x now will need to shift to the denominator. 3 is not raised to a negative power, so it remains in the numerator. Only base of x will shift across the division bar, and now it's raised to a positive 8. So there's my final answer. In the last example, we've got some numerical coefficients again, 5 and 35, and both of those are divisible by 5. So I can start my reducing with 1/7. So I know I'm going to have 1/7 in my final answer. Now I have bases of x, y, and z. So starting with x, x to the first divided by x to the first. Well, those are exactly the same. So when you have a base raised to an exponent that's identical to what it's being divided by, that will equal 1. In other words, it's completely reduced from the problem. So we don't have any x remaining for the final answer. With the bases of y, y to the minus 10 divided by y to the 8th. So those are not exactly the same. They're not going to reduce completely out of the problem. So what I like to do to have fewer steps is compare those exponents. So I really just want to compare negative 10 with positive 8. And whichever one of those is the smaller number, that is the term that needs to shift so that my final answer will have a positive exponent. Negative 10 is the smaller. So negative 10 is going to shift down. So I'm keeping my y to the 8th that was already there, and joining that will be y to the positive 10. Remember, when I shift y to the negative 10 across the division bar, the sign of the exponent changes. Now let's use that same process for base of z. I'm comparing a negative 7 with a negative 5. Negative 7 is smaller, so negative 7, okay, z to the minus 7 is the term that shifts. So I already had z to the minus 5 in the denominator, but now z to the positive 7 will also be in the denominator. And now we're ready to simplify. So the only term I have in the numerator is 1. We must keep 1 in the numerator. You can't just pretend it's gone. We're going to have a fraction for the answer, okay? So we must keep 1 in the numerator. We also have 7 in the denominator, and now we're using product rule. Y to the 8 times y to the 10 is y to the 8 plus 10. That makes y to the 18th power. And then bases of z, negative 5 plus 7. So we're going to have base of z to the power of 2. And here is our final answer. So just take these step by step. Don't try to simplify too many things at once. Just take one base at a time.